So, thank you to all the speakers today, because it gives me an opportunity to kind of do what I'm doing here, to use their insights and the questions that they brought up to sum up a lot of what today in this conference is about, which was partly my request to be with us today. But also because the work in my lab relates to connecting the threads. This is where most of our work is. So I'm going to, on one hand, do that, kind of do a little bit of synthesis of what you already heard, try to connect to tomorrow's session, which to me is quite important as a motivation, and give you two examples of recent work from our lab which relate to how we think we can get there. So let me start with the last thing, which is relating to the topic of tomorrow, which is synthetic cells. And fortunately, you already got a little bit of a preview of that from Kate Adamawa's talk on Tuesday, as well as Lynn's talk. Both of these talks gave you a preview. And essentially, what you heard there is that there is an ongoing, very exciting and large effort, engineering effort, to make a synthetic cell. To some extent, that has almost nothing to do, perhaps in your mind, has nothing to do with talking about geochemical scenarios and scenarios for prebiotic chemistry, which matches, or these scenarios of geochemistry and can work on other planets, including exoplanets. But to me, it does have a lot to do, and this is where I want to actually give you a sense that building a population of protocells capable to evolve, or a chemical system, which we would call it protocells capable to evolve, is actually a stated goal of what my group and our group of labs have always been trying to do. In fact, this is indeed what we would call a model system. Just like in physics, there used to be a model system or a toy model which we used in order to develop the understanding of the physics of ordinary matter. We need this kind of system in order to understand the nature of life. Many people would agree with that. And it seems to me that something what synthetic cell people on one hand are trying to engineer, and something towards which we are building up from the geochemical scenario is exactly what we are talking about. At least that's my hypothesis. And the only difference between today's talks and tomorrow's talks, or Kate Adamawa and Lynn's talks from Tuesday, is in the approach. In one approach, you just try to engineer it with whatever means you can master. In our approach, heuristically, we are saying, what if we use hints and ideas from prebiotic geochemistry, from what the planets would give us for life as we know it, because that is the vestiges we use, vestiges that we think go all the way to the origins, and then try to put those together to get to the same goal. So I want you to understand that this is, in my mind, personally, a very important connection to the other effort, and we feed from each other and trying to accomplish the same goal, ultimately, with a model system which will be capable for the first time to be used as a tool, not as an actual final goal, to answer some of the questions which we're asking today. Because it will be essentially not a toy model, it's not a model, it's actually a tool, something which everybody in their lab can use to do experiments. This is not a theory, it is an actual laboratory tool to answer some of those questions. And so, the possibility to be very trivial and very simplistic here, I want to kind of drive at least one of those points here by discussing the phases and connections during this kind of process, so that we're on the same page, or at least you feel that we're on the same page. So there is what I call phase one, that is building the monomers and precursors. Many people in the past thought that this is kind of the most important thing to accomplish in the origin of life research. If I can build all the building blocks for life, as we usually say in our proposals, then I'm done, because they self-assemble and then life will just happen. Well, I don't think it just happens, because then there's the issue of assembly, and more important, the issue of once you've assembled something, or something was self-assembled, do you have enough opportunity to explore gene space? You have to actually see a phase 2 in which that chemical system, which we call protocells, just for shorthand, is exploring gene space. Whether that's the RNA or you found a better solution for your genetic molecule, that's not the point here. The point is that you do need that phase, and that phase may take a long time, and certainly longer than phase 1. And so you have this now dependency on the supply chain. Phase 2 cannot really function without phase 1 being very robust and available. So from a geochemical point of view, that requires conditions on the surface of the planet which allow you to be robust like this. From the point of view of phase 2, that requires opportunity to actually use those monomers to achieve the ultimate nirvana or phase, which is the self-sufficient protocell. That is one which no longer depends entirely on the environment to feed it all the monomers. This is what we call life today, and as we know it, but it's very important from an astrophysical and planetary point of view. Because phase 2 could happen on many planets for a few hours or for a week or two. You'll never detect this astrophysically, and you'll never see evidence for this happening in the geological record. Probably happened on the early Earth or even on Mars, but it's kind of one of those things which comes and goes. It's chemistry, and it's chemistry which is not robust enough to leave signatures. So you have to get to self-sufficiency, and that probably takes time. And more importantly, you need the model system, which is really what I call phase 2, in order to really even understand how do you get to the self-sufficient protocell. That is the tool I was mentioning. So you need an experimental tool. It is not a theory. And that's very important also from what Lauren said today. You know, it allows you not to get captured by your own models, because phase 2 is not going to be a model, it's going to be a laboratory tool. And so obviously the self-sufficient one eventually will not care about this. And this is the moment in which geochemistry is less relevant. So our thinking is try to get the supply chain understood with the help of geochemistry, and this is our approach. If our colleagues like Kate and others like Petrashvili, and of course in our own team Juan Perez-Mercader, manage to get their full version of phase 2, that will be great. So then we'll concentrate on the prebiotic aspect of it. But I think we're in a good constructive competition there to achieve the same goal and understand ultimately and create that tool which will be useful to everybody. So I mentioned the word robust several times here, and this is what I want to concentrate for the rest of my talk. Robustness is really important in the sense that it takes time and it requires this supply chain to be really there for the budding protocells which are going to develop enough self-sufficiency enzymes, in other words, and ways to produce their own monomers. It's, however, also a very wishy-washy concept. What is exactly robust? You know, like high yields, obviously, changing conditions. I'm going to try to show you with experiments what that means. Also, you can think of it as what we do in the lab. If we usually complain that a lot of the prebiotic chemistry is done by very skilled chemists, and that this could never happen under natural conditions. In my lab, robustness is defined by me that even if Dimitar can do it, then surely it can happen in nature, because I'm actually a negative anti-robustness effect on the chemistry. So despite Dimitar, it happens. So it must be very robust in nature. So one aspect of this will be the ability to see the available feedstocks for this chemistry in the planetary environment. And David and Paul and others talked about this and showed some of this already. that there are stages in which probably you can accumulate that. We are actually sure that this can happen under many of rocky planet conditions. And then you can use what was stockpiled to have a supply chain which potentially can work robustly for a long period of time. And as Ben Pierce talked about that, this needs to be confirmed by experiments, and yes, we have to make sure that all of these stages work well for the superficial type of scenarios that people are developing for chemistry. And just to take one of those as an example, because you heard about it this morning from John Sutherland, it's actually his. Just as an example, again, this can work for any superficial. My arguments are more general than just the specific chemistry. You have a lot of steps here. And when you have a lot of steps, even just to drive this chemistry, you have to be careful. So for example, from hydrogen cyanide to the first useful chiral molecule, which is glyceraldehyde, you need at least 7 steps. The chemistry is driven by electrons. These electrons are driven, photoelectrons driven by UV light. You need the reagents in those lakes or somewhere on the surface which will produce the electrons. Fortunately, we have several possibilities. Ferrocyanide is a very good one. Magnetite is another one. There is also sulfur compounds which produce them. But, you know, that's one thing to remember here. You need low energy electrons as your reducing agent. So it's a reducing chemistry. And most of this will be some sort of reducing chemistry. And the electrons are the agent for that chemistry. And the second thing is there are a lot of steps. Ultimately, you have to feed the protocells. And what these protocells are essentially what Jack Szostak's lab is trying to do, which is at the bottom here. You start at the top with your nucleotide synthesis, but you have to get to the non-enzymatic RNA templating copying. And this is kind of the way I see the problem of accomplishing this in terms of robustness. The supply chain again. How do you get to completing phase 2? You have to solve at least these 3 challenges. Homochirality, thanks to Ron's talk before me, now you know what this is all about. Then activation, you have to create not just the monomers, but they have to be in activated form. You heard Matt Powner early on and others talk about the activation. It's a big topic, has to be resolved in each one case. And of course, ultimately, the non-enzymatic RNA replication. So let me just give you the 2 examples. The first one is homochirality. How do you solve that challenge? Remember, homochirality is a challenge just because we want to know the mystery of life, as Ron pointed out, and Lauren, but there is the second problem. Look at this again. It's a reducing chemistry, but many steps. There is no prebiotic chemistry which will accomplish the origin of life in 2 steps. It will be always multiple steps, and from what we can tell, it's more than 10 or 20 even. If you have multiple steps, you have a problem which chemists who work in industrial synthesis call the arithmetic demon problem. At each step you have a certain yield, and as you have many steps, even if you have a yield which is relatively okay, it's less than 100%, but your final yield depends on the power of those steps, you know, n is the number of steps. Now take a number which is less than 1 and put it to the power of 25. Tell me if you get anything which is different from 0. So that's the problem. So you have to solve that problem in prebiotic chemistry, and people sometimes don't pay attention to that, so I keep insisting on it. You have to find ways to tame the arithmetic demon. The trivial one is, all my steps are high yield. This is wishful thinking. The second one is you hope that there will be crystal stages, there will be stockpiling on the way, so you will break up your long sequence into pieces. That's almost wishful thinking. Actually, it's useful, but doesn't solve the problem. You need all of the above, plus eliminating undesirable byproducts. I spent 5 years in my lab and still working on killing isomers with UV light, but the racemization always got to me. And that was a problem, because you get lost in the end. And that is a big problem, so you have to solve the origin of homochirality. And there came the solution. You heard Ron Naumann talk about the chirally induced inselectivity. He was too modest to say that he actually discovered this effect not a long time ago. Was it 12 years ago or something like that? So we took it with my student Furkan, whom you see here, and go and see his poster, and used it upside down, which fortunately Ron didn't get upset about. Instead of using chiral molecules, we actually wanted to synthesize chiral molecules by using the spins of the electrons. And the idea here, I don't have to fortunately explain to you what the cis effect is, Ron just did much better than me, is that there is a difference in energy, and that difference in energy, including the penalty for flipping, which he explained very well, the B flipped is that penalty for flipping, is also affecting chemical reactions, and particularly that cascade of electron-driven reduction chemistry. The electron being the reducing agent, the actual particle which does this. If you look on the right-hand side here, you know, this is the reducing chemistry, just textbook example of what we call reduction, from oxidized to reduced, reductant to oxidant. And because of the cis effect, you have this small difference, energetic difference, but it turns out it's huge when you have a reduction chemistry going on. So this isomer is reduced faster. Go and see the poster. Furkan will explain to you in terms of the actual prebiotic chemistry how this works. This was a suggestion a few months ago when we published it, a hypothesis. Now Furkan has done a lot of experiments. Actually, the experiments show that it works even better than we anticipated. So go and read the paper, see the poster, and Furkan will explain to you. What I want to point out now is that how does this match in the prebiotic scenario that you've heard on the first couple of days? The way it matches is that we knew all along that these early reservoirs of water, whether it's the ocean or lakes or anywhere on the surface of the Earth or rocky planets, will be very rich in dissolved iron. And so when they are rich in dissolved iron, eventually that iron sediments in different types of oxides, but the different types of oxides. And particularly John Krotzinger insisted in this paper, which we wrote 2 years ago, to have this diagram because he had a very good experience about this redox stratification observed on Mars. Why on Mars, you would say? Because on Mars, it was plain and simple, unlike the early Earth, where we don't have as many well-preserved examples of this kind of prebiotic lakes. We don't. On Mars, though, you do. There is one of them. You can see these deposits very nicely on the surface of a Gale crater in the place where now we know sometime in the distant past of Mars, there was a lake which is redox stratified, and where the bottom layer, as they actually showed with measurements with the rover, you have very magnetite-rich sediment. And this is exactly what you can use in that cis-related reduction chemistry. Again, go and see the poster. The question was, how significant is this when you apply it in real life conditions? We can't go to Mars and get those samples back here for Furkan to measure in the lab, but we have an example of that in the early Earth, not unfortunately as good as Mars. It's called the Tumbiana Formation, where there is there used to be a similar lake. And fortunately, we got a sample just 3 months ago by Roger Fu. So now we will be actually able to study these magnetite layers and use them literally to do some of these experiments. So again, going back to the 3 challenges for completing phase 2, homochirality may be on the way of being resolved, at least for those superficial scenarios. You know, it obviously does involve surfaces as well as you know, availability of shallow water. But when it comes to activation of non-enzymatic RNA replication, our work is related mostly to worrying about the fact that once you have accomplished all this, including homogeneity due to homochirality and getting rid of enantiomers, which are not isomers, which are deleterious, then you still have to deal with this balance between UV damage and UV self-repair. And this is where we have a whole other set of projects going on, in which we are trying to understand the role of UV light in actually sculpting that early molecular inventory, homochiral inventory, by selecting oligomers with UV-induced self-repair properties. So what is the self-repair? Essentially, it is the ability to use UV-induced charge transfer states, electron transfer states, if you want to think of them this way, in the already produced small polymers in order to achieve the earliest possible functionalities before there were enzymes to do that for you. So, in other words, you actually can find switches, early examples of switches, which are affected by whether you have light or you don't have light, which provide the functions, some of the functions which, for example, John Sutherland was explaining to you with the overhang for the aminoacylation of the potential prebiotic tRNA. If you notice, there were two UU quite often at the neck of this overhang, and you can control them with charge transfer states, whether to achieve or not to achieve that particular reaction. It's a very exciting possibility, and we use our laser pump probe equipment to actually do that because it requires the study of the vibrational as well as electronic states in those molecules. So Corinna Kufner is the person who actually works on those vibrational states by using our system. And thanks to the National Foundation and Science Foundation, we actually now, for the last few months, have that. And Corinna has already shown this working in some of those first example of RNA self-repair that you heard John describe to you at the origin of translation this morning. So I'm not going to go into the details, but the self-repair is dependent on what is the exact arrangement of the bases, and that is a very interesting switch which can be used to try to understand that origins. So as a summary, we're close to solving phase 2, I hope, with the help also of our synthetic cell, and we need to do it in order to start this answering these questions, because we need a model tool, model system, a toy model, which we can use in the lab, or everybody can use in the lab. Otherwise, we'll be in the grass there of this Go-Kart energy, and we will never be able to have the tools to kind of rise above the grass, so to say. In the deterministic part, we should look for science in it, on Mars or here on the Earth. Thank you.
So really nice talk. I, from a physics background, really like the toy model idea. I kind of had a naive question actually about the number of criteria that you need to move on to the next phase. And I was wondering why cell replication and cell splitting wasn't part of that. Do you not need that in order to create new generations and everything else? Is there a different way to do that, or is there some other reason why that's not where it is on the list?
Thank you, Paul. I need a telescope in order to see you from here, but that's a big very good question. And you know, Jack Shostak spent about 10 years in his lab working on cell growth and division. He feels that once he gets non-enzymatic RNA replication, the different tricks that he learned along the way will help him do that, and it will work in terms of creating populations, which will then evolve and will be able to use them as this model system. However, there are a few unresolved issues, particularly the feedback between the self-replicating RNA in the middle and the connection to the lipid membrane. And recently, we've started working with people like Petrus Wille and Kate Adamawa to actually use sound insights from the synthetic cell side of things. And even if it's a little bit artificial at that stage, I wouldn't mind that, because it will be a model system, even if one or two of those final touches are artificial. But we have to solve the non-enzymatic replication first. And at least to the people like Jack who are doing the non-enzymatic, trying to solve the non-enzymatic replication problem, the cell division is an easier problem that is almost solved at this point.
Okay.
That was fantastic, Dimitar. Particularly, I'm glad that you're working on the UV part, so I've been worried about that for a while. But really, what you're delineating there is your transition from step 2 to 3 is a question of defining life. And of course, step 3 is not completely self-sufficient. There's no organism short of, even some photosynthetic organisms that approach self-sufficiency. No one's really self-sufficient. So at some point, you've got a movable line there. I was just wondering, have you thought about where that transition zone is where you're going to declare success?
Lynn, this is the $1 billion question, maybe. We need $1 billion to solve it. No, this is my favorite question. Now, my feeling is that we need that model system in order to answer your question. So if we get to the one which is completely dependent on us to feed it with all the phase 1 supply chain, then we can, help it grow and get old and, like a parent, and see what happens. And then maybe we will know, at this point we can call it self-sufficient enough so they can leave the apartment and live on their own. You see what I mean? I don't have a good insight on that. I know John and Jack like to speculate on this. I know certainly all of us like to speculate on this. Maybe this is exactly what I'm trying to drive. Let's build the model system and then try to answer your question. But on the other hand, if we make phase 2, I know that any of us who makes phase 2 will like the front page of the New York Times to say, we finally made life in the lab. But to me, that won't be correct. I don't think we can call this life. Phase 2 is not life yet.
How do you know you get to phase 3?
I don't know. I don't know how to know. But I hope that phase 2 will find it.
So using the chair's prerogative, I think in the other Dimitar's talk, right, Dimitar Kunev was suggesting that was when you have this feedback between the information and the structure in that self-perpetuating replication.
Yeah. So this is what I was trying to say in my answer to Paul's question, is that the cell division is a difficult problem, and without cell division, growth and division properly, as Kate Adamawa also pointed out, you're not going to have possibility for proper evolution on the cellular level. And so the question then is, do we know how to make this feedback? So maybe it's Dimitar's answer, or maybe it is some other way to do that, but you have to find some way, let it work, and see then whether it answers your question.
Anton.
Yes, so I have a question on transition between phase 1 and phase 2. Great talk, first of all, very ambitious project. So my question is on transition from phase 1 to phase 2 on your schema. So my question is, when you define phase 1, do you imply that there is a variety of all different kinds of prebiotically plausible molecules that you're dealing with? And if so, then do you have a process that would define emergence of RNA or DNA molecules, or you assume that this is something that happens for granted?
That's a very good question, Anton, and thank you for asking it again. At the minimum, you could say something like this working in a flow system, like Herbie pointed out today, is the minimum you need. What the people like Jack Shostak were trying to do at the bottom line of this diagram will tell you that it takes more.
No, before getting here,
Yeah?
there is a library of 100 plus different types of prebiotically plausible nucleobases that would be generated. So that's what I'm asking.
Yeah, so that's, Tom, that's exactly where I was going actually. Because in what Jack, for example, is doing, he's trying some of those. We are trying some of those too. I particularly like inosine, for example, which is non-canonical, but some people don't. The point is, we don't know the answer yet. That's why phase 2 is not built, I suppose. I'm perfectly happy to work with inosine in the beginning, even though it's not canonical. That was my point, is if you, I don't want you people to think that we're only going to do canonical phase 2. We're happy for it to be non-canonical. But what you're probably asking is, do we want to go even further than that? That is, go to the stages, the phases that you described. Of course we do, but we think some of the issues and questions you were asking in your talk will be easier to solve if you have a system like that in which you can turn the knobs in your lab. So that was kind of where I felt there is a very good connection with what you guys are doing and what we are trying to provide you with that tool.
Dimitar, you talked a lot about motor cells. But if you go to synthetic biology, cooperative effects are extremely important. So where are the cooperative effects in your whole scheme at the moment?
Are you talking about cooperative effects in biology, Thomas?
Yes, and actually on the subcell level already. So if you go to synthetic biology, you will see a lot of these cooperative effects, and they seem to play a big role. And it seems to be that you're mostly talking about a kind of individual cell, which is a very artificial construct.
It is a very artificial construct, but Thomas, it will be easier for me if you give me one example of cooperative effect, because some of the chemistry that we see here, the interaction between groups of molecules, appear like cooperative.
Yeah, and imagine two fluid spheres, and they start to exchange the content, and then one grows and one dies, and you can do that, of course, with much more ingredients, and then you get a cooperative phenomenon instead of an individual object you're looking for.
Yeah, so this type of cooperative effects, again, I think will be beneficial to have the model system that I was describing. So that is actually where Petrus-Wille and I are talking about, is that could some of the work that she's doing, where there are a lot of cooperative effects in where she's trying to develop the functionality of cell division from a synthetic cell point of view, she sees a lot of that. In fact, that's one of the challenges that she has. Could we actually meet in the middle somewhere, where our cooperative effects are more on the physics, chemistry, like at most the cis effect level, while hers are on the system level, which is much larger structures, like what you're describing. I think that's not a solved problem. And in fact, that is probably the challenge of bringing those two communities together. What you're going to talk tomorrow, plus compared to what people are describing today.
Okay, so let's have one last question before we move to posters.
Dimitar, the scenario that you present is a fascinating, natural, aqueous geochemistry system, but it has peculiar properties in an early Earth or early planetary context. Because there are these three classes of iron-containing proto-minerals, or ultimately minerals. The oxides, right, like magnetite, magnemite, and also the hydroxides, like goethite But there are
It's
also
also graphite.
and there's greigite, but there's also the sulfides.
Mm.
Now, these things, which ultimately lead to pyrrhotite, for example, and each of these, I say, are peculiar because they're paramagnetic or ferromagnetic. They also begin as colloids. They're cryptocrystalline. Before sitting in sediments, they recrystallize to form the end product magnetite and pyrrhotite and so forth. But they also have photochemistry. Because in the oxidation of Fe2+, a UV photon can come in, knock off an electron. It makes it reactive, then insoluble, and then you get essentially a fractal particle of ferroferric oxide that falls out, and it's magnetic. Then, the sulfide example, which leads you to pyrrhotite, is just as fascinating because the sulfur in there was in the atmosphere, gets photochemically transformed. You have a mass-independent fractionation of these sulfur reservoirs. The reduced one, the S8 or whatever polymer, hits the water, it reacts with iron 2, makes protopyrrhotite. It's also a colloid, fractal particle, and it's magnetic. So there's a rich magnetic chemistry there, and I'm wondering, are you going into the sulfides? Are you going into the hydroxides in this investigation of the ability to confer, for instance, chiral character on your reaction products?
Thank you, Stefan. And that's actually why I wanted to talk to you. But this is a very good point. So you made an excellent point and I have two answers to that. The first one, I'm very, very interested in what we are doing in our labs under the title of Dirty Water Project. So we are mixing up all these things which we think were there and seeing whether any of them is a showstopper to any of that chemistry or any of those mechanisms that are in the simpler versions of the scenarios. Number one. Number two, what you're describing with the variety of possible magnetizable sediments, colloids, and potentially future surfaces is actually makes us really happy, because ultimately the cis effect is not about the magnetic field. It is about materials which can bias their electron spins near the surfaces, as Ron explained. So that gives you a plethora of opportunities for cis effect or related electron spin related effects, which I can't tell you all about that, but you should go and talk to the Furkan, the poster. The experiments actually exactly confirming what you're saying. Anytime we have some bias in the electron spins, the chemistry goes better and purer. And you know, it goes one way or the other, but it's pure. Purification and homogeneity, which everybody was talking about today, is very important, and spin effects help. So what you're saying is exactly, so far, is going in this direction. Is there a possibility for a showstopper? Absolutely. Before we finish, I cannot say with certainty that this will work, but at least for the time being, all of that goes in the same direction, helps.
Okay, so if you have further questions, Dimitar is going to be around, so you can speak to him in person. So let's thank him again for his